so you can, we'll all move up there for further discussion after the talk. But I think for now, I will introduce our speaker for the evening. Everything okay, Angus? Good. It's my delight to introduce Professor Jane Evans, who's recently retired from BGS. And she is a geologist who has dabbled in archaeology for about the last 25 years, a bit more than dabbling, so you'll hear more about that later. But she's worked on everything from Welsh slates to Chinese granites, mainly looking at the isotopes in there. And it was about 25 years ago that she started looking at the isotopes in archaeologically significant things and applying the geological techniques to that, including she managed to get a tooth from Richard III's skull and did work on that, which has made quite some news. But she's also been on the telly. You may have seen her on Meeting the Ancestors or Digging for Britain or working on the Tony Robinson podcast. So we're really privileged to have Jane here live in person and online for our Zoom audience to give us a talk tonight at the Edinburgh Geological Society. So hand over now to Jane.
Okay, can you hear me? Yes, fine. Okay, so as Alistair said, I am a geologist. I started my career in the British Geological Survey in the early 80s. And the main job I had then was using isotope geochemistry, and I'll explain a bit more about that later on, to primarily date rocks, trace their origins, look at the sources of sediments and this kind of thing. And then about I suppose 25 years ago, archaeologists started to inquire into our laboratory as to whether they could apply to use the isotope systems that we were using in geology to apply it to archaeological problems. And so it was things like, you know, using lead isotopes to trace metals, could we source glass? And in particular, could we look at tracing human individuals using their teeth, which lock in certain very useful elements. And I thought this was fascinating, and this was early days, and I thought, well, this sounds like a really interesting sort of area to get into. And so I hope, jumped in and sort of had a go, so to speak. And for the last 25 years, I've been collaborating with a large number of archaeological departments across Britain. And after a few years, I started to work with an archaeologist called Mike Parker Pearson, who focused a lot of his work on Stonehenge. And he was interested in getting involved and developing some more work on the Stonehenge site. And to be perfectly honest, as a geologist, I looked at this and I thought, what more is there can you do? It's a bunch of stones, okay? We've done the geochemistry, you know, what more can you know? And so this talk is all about how utterly wrong I was in that assumption. And I'd like to go through some of the research that's been undertaken in and around Stonehenge in the last 20 years. And so I thought I'd start with summarizing the work that's been done on the actual rocks and stones. And then I'd move on to looking at how we've tried to track and trace those people who were trying to build, or we think might be the builders, the creators, the architects of Stonehenge, and explain how we've applied these geological tools to these archaeological problems. So a brief background, first of all, of Stonehenge. I've got Alison sitting here, you know, and I'm thinking, I better get this right. So about 3000 BC, they think that the initial site at Stonehenge started to be created, and it was created in stages. And the first stage was that they built a huge circular ring and ditch. And inside that, they put wooden posts, big posts. After that, a ring of stones was put in, what are called the blue stones. And then after that, sometime later, the big 30-ton sarsen stones were put into place. And so what I'm going to look at is some of the research that's gone on these different stones. And I'm going to start with developments with the Sarsens, because Stonehenge was given to the public, I think, in the 1920s. And so the first thing that had to happen was they had to make sure it was safe for the public. So construction or sort of support work was done to make sure that it was actually safe to walk around. Then more work was done in the 50s, and they decided to re-erect one of the trilithons. Now, when they did this, they discovered that perhaps they weren't as smart as the Neolithic people who originally built this, and they couldn't get the structure stabilized. So they drilled in to the uprights and put a steel posts in to hold it in place, okay? Now, this was all been and done and probably either not known about or forgotten until 2019, when a letter arrived to the managers of Stonehenge or whoever, or English Heritage, saying that one of the guys who'd originally been involved in this engineering had kept the core that had been taken out of the stone. He'd moved to America. It was his 90th birthday, and he asked his son to repatriate this core, which was about 1 meter long. This is what it looked like. And so this incredible sample of the internal aspects of one of the Sarsens came back to Britain. And this enabled us to analyze the stones. I think we were allowed about 1 centimeter in total for destructive analysis. And it was sort of done to death in terms of geochemistry, isotopes, petrography, sedimentology, the whole lot. And a big paper was written that basically characterized it. And although in a way it didn't perhaps teach us a huge amount more about what the stone was, it did pinpoint for us. We were able to pinpoint exactly where these Sarsens came from, which was about 30 miles north of Stonehenge. This was known in general, but this really pinpointed it. But one of the things that struck me, and I think other people, was when you see the color of this stone and the nature of it, uneroded, not covered in lichen, and the stones are a pale sandstone that was silicified. So if you can imagine this stone upright, fresh and clean and dressed, if not polished, it's going to be a huge white or slightly off-white, if not reflective, sort of beautifully sort of reflective, I suppose, type of structure. And this tells you perhaps what this structure looked like when it was first put up. So that was the news about the Sarsens. And in fact, this is a picture of, I think it's called the West Woods. West Woods, yes, where these are the original stone slabs that were transported down to Stonehenge. Now, inside the big outer ring of 30-ton stones are these smaller stones, these here. And these are called the blue stones. And geologically, they are totally different. These are predominantly dolerites with some rhyolites. And again, in 1924, when the first work was done on these, and they were still allowed to cut sections and look at the internal structure of these rocks, it was discovered that these dolerites were matched with a location in South Wales. It's really quite a distinctive texture. It's called the spotted dolerites. And I think a geologist at BGS matched it using thin sections from probably the BGS collection. And this, of course, then precipitated what one might call the great debate about the fact that these stones, these 7-ton stones, had been moved about, I think it is 240 kilometers from Preseli to Stonehenge. And this debate continues on how this was done. And there continues to be a lot of debate about this. It used to be thought that glacial transport was involved in getting these stones, but by and large, it's felt that the glacial directions are wrong, and there's no evidence that there are other stones from Wales anywhere near Salisbury Plain. There was then talk of them coming perhaps on rafts up the estuary. And I think nowadays they think it's most likely that they were transported on sledges. Now, while they had identified where the bluestones came from, or the dolerites, the rhyolites remained uncertain. I mean, while it seemed probable that they came from a similar place, a rhyolite is a far harder rock to provenance petrographically. You know, it's pretty homogeneous, it's sort of rock. But a geologist from Cardiff, Richie Bevins, working with Mike Parker Pearson and others, started to investigate. They could do XRF on the stones in Stonehenge without damaging them. And they started to survey all the possible outcrops that they thought could supply these felsite stones. And they came across a place, an outcrop called Craig Rosivelen, which again is in South Wales. To me, as a geologist, this looks like one of many, many outcrops you can come across. You might fancy climbing up and that you find in Wales, you know. However, when you release archaeologists onto something like that, as opposed to geologists like me who would lay into it with a 10-pound sledgehammer, archaeologists dig around it with trowels, and they do these amazing excavations. And they found, I believe, wedges left in some places here where they were going to lever these jointed structures out. And in particular, if you look here, you can see that this slab is actually on a sort of trestle structure. And in and around it are the remains of charcoal, where they used heat and water to kind of break and shape the stone. And more amazingly, as they excavated down here, they also found charred hazelnuts, where somebody sat and eaten hazelnuts during the excavation of this structure. So they did carbon-14 dating on the hazelnuts. And what came out of that was that these stones were being quarried approximately 500 years before the creation of Stonehenge. So they then had the theory that these stones were quarried out, that they were erected as a stone circle nearby in Wales. And then later on, this stone circle was moved to Stonehenge. And you're talking about moving, I can't remember, 40 or 50 stones, I think. So that again was completely new information about the movement, the sourcing, and the origin of the bluestones at Stonehenge. Now, there's a picture close up, and you can see how this is basically sitting so that it's horizontal. It's wedged up on this kind of trestle. And you can see also where possibly it's been chipped away and dressed, or partially dressed, but obviously this one was never moved. And in fact, I think there are similar examples in Scotland near some of the Scottish circles of slabs like this on trestles in a very similar orientation. It was obviously the method they had for prepping these slabs before they moved them off. So the final stone I want to talk about is the altar stone. Now, the altar stone is this very much hidden structure here, okay? And the altar stone is made of old red sandstone. Now, again, there is old red sandstone all over Britain. And it has always been assumed that this old red sandstone had been collected effectively en route from Wales to Stonehenge, and that it probably came from one of the Welsh or borderland deposits of the old red sandstone. However, again, Richie Bevins, who's very interested in all these rocks, started analysing and looking at the composition of the altar stone. And he found that it had within its matrix quite a lot of barite. And when he went and looked at the Welsh and the Southwest England old red sandstone deposits, they didn't contain any barite. And so he started to look further afield and was interested in where you might get barite bearing old red sandstone. So he teamed up also with a group from Australia who decided that they would be able to make what's called an age profile on the sample, on the sandstone. There were a couple of thin sections that had been cut again previously and held in a museum, and they were able to take those thin sections and look at the zircons. Now, let me explain what they did, because it's not a straightforward process, this. The old red sandstone is deposited in basins across Britain, and it's locally eroded. So what you're going to find is that the erosive sources of the stuff that goes into the basins in Scotland is going to differ radically from the kind of rocks that are eroded in Wales and the kind of rocks and the age of the rocks that are being eroded in Southwest England. So you erode the rocks and you deposit them in a basin. In eroding those rocks, they often contain a mineral called zircon. And zircon is one of the critical minerals for dating because it crystallizes with uranium in its structure, and it is extremely robust, and it survives all kind of tectonism and reworking. And so what you do is you date the zircons in the sediment, and you're going to get a profile of different ages, because it's not just one granite that might be eroding. You've got a bit of this and a bit of that. But what you get is you get a profile like this of the various ages in that sediment. So they did that for the altar stone thin section. Now then they need comparative data to look at the profiles found in all the other sandstone basins in Britain. And fortunately, that research had been done and was published. And so they could start to match the profile that they got out of the zircons in the altar stone with the British outcrops. And they found that the best match was with the sandstones of the Orcadian Basin, and they looked in Orkney and matched it. And the paper that came out suggested that the altar stone had been brought from Orkney. Now, I've just said I think the Neolithic people are very clever, but I really do think that it would have been extremely unlikely that anybody could build a raft that could get a 30-ton stone across the Pentland Firth safely. So very rapidly, I think other people thought that. And there was a second paper published that suggested that, no, it probably wasn't Orkney, it was from northeast Scotland. So you only had an overland journey. Now, that still means you've got an overland journey. And again, the great debate is, you know, how do you do it? And I think we come back now to, well, you know, maybe we don't know as much as they did, because these are the people who shifted stones 200 kilometers from Wales. And frankly, if you can shift it for 200 kilometers, it just takes perhaps 4 times as long to shift it from Scotland all that distance further. Now, again, there is talk about whether for part of the movement, they might have gone round the coast or down the rivers. But my personal feeling is, having thought about losing your stone in the Pentland Firth, is if you transport something on any depth of water and you lose it, you've lost it. Whereas if you bring it overland, it may be a lot of work, but you're not going to lose it. And so I have to say, I agree with those people who think that they probably just used a system of sledges and dragging. Now, there has, again, it's always been assumed that these sledges were drawn by people, largely because there has until quite recently been no evidence that animals were used as beasts of burden in the Neolithic. But there have been a couple of studies recently, one from, I think it's Ireland, where they show that the structure of an ox's hoof suggests that it has got weight-bearing on it. And there was another one where I think, I might have got these the wrong way around, another one where they showed that animals were being bred to a larger size, which again, they also think may be due to using them as weight-bearing. So there's becoming a possibility that people think they might have used oxen of some type to help drag these stones on sleds. And of course, it's still ongoing research, but that's where we are. Now, a couple of things that I find fascinating is, I've often found this, the minute somebody sticks their neck out and says, God, you know, this stone, it can come from Scotland, you suddenly find people going, well, of course, they found a mace head made out of the Lewisian gneiss in Stonehenge. So they've obviously had some communication with Scotland. And then somebody else goes, well, do you know, the shape of the houses that they found near Stonehenge are remarkably similar in structure to those that are found in Orkney. And finally, there are apparently carvings and impressions of axe shapes on stones in Scotland that are also mimicked on some of the stones in Stonehenge. So suddenly, from this, well, for goodness sake, you know, who would expect communication over that distance? You start to pull together quite a bit of sort of supporting evidence. And I think that's quite an interesting question. And it certainly becomes interesting when I go back to some of the other stuff I'm going to talk about. So of the stones, one of the things that strikes me about this new work is that you need to think now of Stonehenge. Think of it when it was new. It was founded on chalk, which stripped of grass is going to be pure white chalk. You're going to have these huge sarsen stones, sort of shining white, or at least if not shining white, you know, with a siliceous surface standing tall. Inside them, you've got these virtually black, blue stones. And in the middle, you've got this bright red altar stone. And it starts to make me think how colourful this would have been if we look at it not from the lichens and the grey and the weathering that we see now, but what it might have looked like when it was originally put together. And again, it makes me wonder about, you know, what some of the Scottish stone circles would look like as well, if they were all sort of polished up and all the various different rock types that were there were really clear. So basically, my first comment on what on earth can you do with the stones is that, well, we've discovered exactly what the composition was from the core that was returned by the Sarsens. We've identified the source of the felsitic bluestones that's from South Wales to the very quarry. Dating the quarry shows that Stonehenge, the bluestones were probably a stone circle in Wales long before they were lifted and transported to Stonehenge. And that the altar stone, far from being a Welsh old red sandstone, is in fact probably from northeast Scotland. And that seems to me to be quite a lot of progress on the geological front from the Stonehenge side. So, having done that, we then ask the question, who built Stonehenge? And I want to explain a little bit about basically a lot of the work I do, which is how we use isotope data to track and trace humans and fauna. And so I want to just give you an analogy without getting too deeply into what isotopes are. But basically, many elements have several types. They come in different weights or masses. So, for instance, you've probably heard of uranium-235 or uranium-238, and these numbers tell you something about the fact that they are slightly different. They have different weights. And these features affect how the elements behave physically. So here's a little example. Supposing you walk into a bowling alley and you walk in and you find on the bowling alley lines, it's only the lightest bowling balls are there. What, the 8-kilogram ones, I think, are the lightweight ones. And the whole place is full and all the big heavy bowling balls are up on the shelves. You can think to yourself, well, how would that come about? And you might come up with a hypothesis, let's say, that there'd been a kids' bowling party. Kids were going to use the lightweight bowling balls. So from there, you have a hypothesis and you can set up an experiment. And you can say, right, I'll put all the bowling balls back on the shelves. I'll organize a kids' party. I'll see which balls they choose to use. And fair enough, all the kids come up and they positively fractionate, as we would say, the lighter bowling balls into the active zone, leaving the heavier bowling balls on the shelf. And you can sort of contradict that and go, well, I guess if the rugby club came in, we'd have the reverse situation. And so the physical processes here are separating the different types of what you might call isotopes or bowling balls, okay? And then your friend goes, yeah, but you know what? When my mum went bowling with her friends, she used all the lightweight bowling balls as well. So you can't tell the difference between whether it's in a kids' party or my mum and her friends and her bridge party. So you go, right, we need another variable. Okay, well, how about kids drink orange juice and mums drink tea? So if it's lightweight bowling balls and orange juice, we can exclude the mums. And if it's lightweight bowling balls and tea, we can exclude the kids. And that's the basic principle on which we do our studies. We build up a stack of situations where we can exclude certain options because the process doesn't work for that particular hypothesis. So with that in mind, and I'll go back to this a little bit, I want to talk about how we look at human skeletal remains. And I'll start by saying that when somebody is buried, basically diagenesis will affect the bone structures, but they don't affect teeth. And so teeth, because they are basically a mineral, they're apatite, bioapatite, they retain the life signal of the individual. And teeth contain some very useful things, such as strontium and lead and oxygen. And all these elements have isotopes in them that tell us different processes were in action. So what we do is we layer up the analyses to try to restrict where a person could have spent their childhood. And I have to say childhood because, of course, your teeth form in childhood. And basically, the last probable point of mineralization for the wisdom teeth is about the age of 15. So we've got a span from sort of 0 to 15 where we can trace people. But after that, we're a bit stuck. Now, there are people buried in and around Stonehenge, but not that many. And there's a sort of sense that it's unlikely that they were the original builders of Stonehenge. For instance, a fortuitous discovery some years back, well, I think a gas pipe or a water pipe was being put in, was that this skeleton was unearthed. And this guy has been called the Amesbury Archer. And he's a Bronze Age burial, and it is the richest Bronze Age burial that has been discovered in Britain, as far as I know. He had the most magnificent set of arrowheads with him. We had the gold tresses for his hair. He had flint wrist plates, which we think are to do with archery. He had 3 or 4 bronze knives and about 7 urns or pots in his burial. It was an amazing burial. This is a reconstruction because when they realized what they were excavating, they excavated through the night to make sure that nobody could damage the grave. So there aren't many photos of the actual excavation, but this is the reconstruction of how he was found. And so we were asked to look at his teeth to see if we could tell where he spent his childhood. And we did strontium isotopes, and strontium relates to the land. And I have to say, we got a fairly ambiguous value. I could rule out parts of Scotland, parts of Wales, but it wasn't a terribly diagnostic result. But when we did his oxygen isotopes, he had quite an unusual value. And in fact, his oxygen isotope values plotted within this zone, okay, which placed him anywhere between Scandinavia and really down to the Alps, and clearly not British. Now, the funny thing is, of course, that archaeologists don't get money to fund boring studies. They get money to fund interesting studies. So this was an interesting study, but the problem we had again was that we had very little reference data at that point, because we hadn't been able to get all the work done on all what we'd like to have, which is the big reference data sets that tell you what your average British person has. But through time we did, and we strengthened this argument. And the likelihood is, and it's still a statistical likelihood, but it's quite a high statistical likelihood, was that this individual probably came from Eastern Europe. Okay? So that was a kind of exotic burial that was found. However, now the other burials that were found, if you remember, I talked to you about the wooden posts that were one of the earliest structures that were put into Stonehenge. When these were removed, they were left with holes, which one of the earliest archaeologists looking at Stonehenge discovered, and they're called the Aubrey holes. And in each of these holes were the remains of a cremated individual. Unfortunately, subsequently, when they were excavated again, people didn't really think you could do much with cremated materials. So they collected all these cremations and put them in one bag and reburied them. But that meant we had sort of completely commingled situation. However, because there is a guy who works in Brussels these days who specializes in cremated material, what they managed to do was sort out the fact, for instance, it's like taking the left femur, if you could do it, or you find one part of the skull that you know has to relate to a skull, and you pick them all out, and you then know that you've got a sequence of individuals because you've got the left-hand side of the ear part of the jawbone or something. And they looked at the strontium isotopes there, and they found that quite possibly these individuals could have come in part from somewhere like Wales. But that was as far as we got, okay? So again, there was a loose possible connection, but it's not a guaranteed one. So the next project I got involved in was actually based in a place called Durrington Walls. Now, this is Stonehenge here. And Durrington Walls is a huge circular structure that was discovered some years back. And it looks like that. And this is thought to be the area where probably the people who were either going to Stonehenge and celebrating or involved in the construction or parts of the construction stayed. And an artist's impression of what it might have looked like is this, okay? But the really interesting thing about Durrington Walls is the number of pig remains that were found there. Thousands of pig bones were found at Durrington Walls, which reflects basically feasting and eating. And furthermore, almost all the animals were about 9 months old. So again, bred in spring, slaughtered in winter. And again, I think maybe there was one human remain in that structure, but we had all these pig bones, we had all these pig jaw bones. So we set about looking at the pig bones because we had a very, very simple hypothesis, which was this. Were the pigs bred locally on the chalk for these feasts, or were they not? And the chalk is a very homogeneous structure, a very homogeneous rock. It has a very reliable and well-identified isotope signature. And so if the pigs had been bred in and around the chalk downs of Stonehenge, Salisbury Plain, we would be able to match it up quite well. So to do that, okay, this is what we've said. We could, using this map that we created, we could predict quite well what pigs raised in Salisbury Plain would look like in terms of the signature of their teeth. This map, by the way, is something that we've created as a reference use, because the way you get strontium into your teeth is that it's released from the underlying rocks, forms into the soil, goes into the solution, picked up by plants, and goes straight into the food chain. And its composition is not changed. So what you've got is you've got the strontium signature of the labile or the soluble part of the rock. And simply speaking, it pretty much reflects the feldspar composition if you're in a silicate. And so we can look at, you have a broad relationship between the older rocks having high strontium values and sort of the Welsh ones having middling ones, and then a lot of Middle England having relatively low values. And we can use that as a diagnostic. So how do we do the analysis? Well, we sliced a corner off a tooth on the pig's bone, and pig's jaw, and we always used the same molar. So we've got consistency in the tooth that we're using. And then what I would do is abrade off the surfaces, clean it up, remove any dentine, so that I've got basically a bit of tooth enamel, probably the size of a fingernail clipping or something like that, and 30 milligrams. You take that, and then we dissolve that in acids in the clean room, because what we want to do is we want to separate the strontium that's important to us from the much more dominant calcium, which is the main component of the tooth. So we extract the strontium using chromatography. And I'm just going to suggest that at least I'm talking to an audience who might remember using blotting paper and ink, because I certainly do. And if you remember, you put ink on the blotting paper and then it spreads out and the colors change. That's chromatography, okay? And that's what we do, except we use these columns and we put a solution of tooth on the top, and the different elements move down the tube in different speeds. And we know when the element we want strontium is at the bottom, and we remove the washing and we collect the strontium that we want in a little beaker. That's how we do it, quite straightforward. Then we run it on a mass spectrometer, which analyzes the isotope composition, the various masses that are available in that strontium, and we come out with the strontium ratios, which is what we're after. There we go. Lots of data, And this is what we got. Right. Had they been raised on the chalk, they all would have had a signal something like this. I'll allow them maybe a little bit more latitude. But these pigs and these pigs' teeth basically had a range of strontium isotopes that were equivalent to the full range of isotope values we measured across Britain, okay? So a huge diversity, really couldn't pin many on any particular or exclude any particular origins. So as well as that, we did another isotope, sulfur isotopes. And we had a look at that and we thought, well, we know pretty well what they'd be if they were Salisbury Plain. And yet again, we got a wide diversity of results. I mean, I think we can exclude the fact or show that the hypothesis that they are local is wrong. And if you combine those two things, what you've got is, this is the area where I'd expect the Stonehenge raised animals to be. These animals up here actually have a strong marine component based on sulfur. These animals are difficult to attribute to anywhere in England and Wales because the values are so radiogenic at the time. Now, this is where science clashes with politics. This was a time of Brexit. And basically, we had said that we didn't know where they came from Britain, but they were pretty certain they were British, okay? And the headlines came up. We didn't need to import our pigs in the Neolithic, and we don't need to import them from France now. So basically, again, science rolls on. And we looked at, we were particularly worried in 2019 because we hadn't found out about the altar stone. So we were busy sort of backpedaling a bit about the thought that these animals might be from Scotland. And there was some criticism at our suggestion that we couldn't exclude them from Scotland as well. So we looked at some other methods and techniques. First thing we did was we improved our map. And we now found that if we looked carefully at southwest England, the granites there could, in fact, deliver us the kind of unusual values that we had previously needed to push into Scotland. So we decided that, yes, maybe they still had to come some distance, but maybe not from Scotland. Then had a bash at lead isotopes. Because again, because Scotland is a totally different tectonic structure from southern Britain. In other words, there's Laurentia up here, very, very old basement rocks. But down here, we have Avalonia with a maximum age of about 600–700 million years old. The lead isotope signatures in Scotland go to a much lower range than the ones in England and Wales. So had the animals come from Scotland, I would have expected to see a moderate number with what I'd call definitely Scottish type signatures. And we didn't. We basically found that almost all the animals could be attributed to England, mostly England, and maybe Wales. So we pushed on. And we're still pushing on. Oops. So the interesting point about that is that the pigs didn't trot there on their own, okay? So clearly we feel that this is much more a model of you come to Stonehenge and you bring your animals with you. And so we are looking, what this study shows us is that we are looking at a huge diversity of origins for people coming to Stonehenge, either to work on it or to celebrate. We can't at the moment really exclude many places based on the pig data. What we can say is that it is really quite diverse. The majority might seem to be, well, Wales and southwest England do seem to me to be the most probable primary directions given the combinations of data. But I think we're still working on this. And so what I would say is, my goodness, we did learn a lot in the last 20 years about Stonehenge and the people that built it. And that still goes on. And also the controversy still goes on. So this summer, a paper came out that I worked on looking at the composition of a tooth from a cow that was found at Stonehenge, and seemed to have evidence that it actually had come from Wales. The lead isotope suggested it come from Wales. And I'm just going to put up the response I had from somebody who sent me an email about that little study. I think that's my 45 minutes, so I'll stop there, okay?